Hi everyone, I'm Rohit Kumar Singh, the TA for this course, Statistical Mechanics, and this is the our 11th live session. So this will be the second last live session. We might have an extra session that will be announced later, but yeah. So far we have 12 weeks. So this is the week 11. So in the last lecture we studied how ideal gases behave in a canonical ensemble. Okay, and we learned about the mean occupation number for uh, different types of gases like Bose gases and Fermi gas, ideal Fermi gas, and we learned about the density of states and solved some problem based on that. So today I'll I'll like to recap the ideal Bose systems, so ideal Bose gases, and how we achieve the Bose-Einstein condensation, and what is the criteria for Bose-Einstein condensation, which is a very famous phenomena in physics, right? Okay, but first I'd like to discuss something which is the classical limit. So where does this there is a transition from the classical to quantum behavior for a you know for a system of gas. So the limit, I mean, so if we are talking about a classical system, they should follow this criteria, that this n lambda cube, where which is explicitly written like this, should be less than 1. Here lambda is I have already mentioned it before. It is the mean thermal wavelength, or also called as thermal de Broglie wavelength of the particles. So now you see here, and n is the density, right? Number density. So when it is less than 1, right, that is closer to 0, uh, we consider the system as classical. Okay, that means temperature should be very high, right? For this to get closer to 0, temperature should be greater than 0, right? So high temperature and low density, and this should be 0, right? That means if you have high temperature and low density, low number density, then the system of gases can be considered as classical. But as we move from this criteria, and when this n lambda cube becomes, you know, approximately equal to 1, then the system cannot be no longer can be described as classical, and we need to consider quantum mechanics. Okay. And so this is the condition that lead us to study this quantum statistical mechanics. Okay, so now, so this is I wanted to just mention. Now let's discuss the thermodynamics of ideal Bose gases. Now, in the last lecture, we studied that the mean occupation number for a Bose gas is given by this formula. Right? So this is -1 for bosons and +1 for fermions or Fermi gases, right? And uh, also, if we consider the fugacity, which is e to the power mu by kT, then this formula becomes Z minus 1 okay. Also from the lectures of grand canonical ensemble, we know that the ratio of PV upon KT is given by log of this grand potential, right? Which is also equal to this summation of log of 1 minus Z e to the power minus beta E, and this summation is over all the energy states. Okay. This we studied in grand canonical potential during the grand canonical ensemble discussion. This is called grand potential. And total number of particles n should be equal to sum of the mean occupation number, right? So this sum goes over all the energy states, and for each energy state the mean occupation number is given by this Ne. So this sum should be equal to the total number of particles, right? That is this thing. But now, since we want to consider this uh, quantum behavior, we need to look at the regime where temperature is less than zero, and number density also. So basically, number density increases, right? And that will lead us that will lead to this energy states uh, from being discrete to a continuous spectrum, right? So right now our energy states are distinguishable, right? But as we increase the density, they will overlap, and we will get a spectrum. Okay, and then this summation is no longer valid. Okay, because we don't have now the discrete energy states, we have a spectrum. So we need to consider the density of states that we discussed last time. Okay, and so the density of states is given by this formula, as we also saw last time. So I am writing this in terms of energy of the states. Okay, this is the density of states, and now we will reformulate these two formula for PV upon KT and number of particles. Okay, for a continuous spectrum of energy states. So we need to take this summation, we need to convert this summation into an integral, right? And to do that, we will use the density of state. Okay, so for example, this number total number of particles, instead of summing, we can write it like this. Okay, and this goes from 0 to infinity. Similarly, PV upon KT, we can write it like this, right? This also goes from 0 to infinity. But here is a caveat that if we naively put dE in this two equation, the energy state with E equal energy, I mean the ground state energy state, basically the ground state with energy equal to 0, it will it will be eliminated, right? Because in both the formula, as you can see, this this becomes 0, right? D the density of state becomes 0 for E equal to 0, right? Because you have a square root of E dependence. So what we will do, and we know that this ground state also contributes this ground state also contributes to this you know, spectrum of the states, right? It also uh, has a occupation probability, so we cannot just, you know, ignore this. And if we just calculate the integral from 0 to infinity, the E equal to 0 state will be eliminated. So what we will do is, uh, we will isolate this ground state from this summation, and then we will perform this integral. Okay, so basically what we will do is, first from these two equation, we will isolate the E equal to 0 state, okay, and then perform this integration. So let me write what I mean. So I'm basically saying that, first let's put E equal to 0 here. What you get? Yeah, 1 by z inverse e to the power beta e becomes 1 minus 1, which is nothing but 1 upon 1 by z minus 1 this quantity, right? So this is the ground state occupation number. Sorry, I mean, yeah, the number of particles in ground state. Okay. Or we can write it like this. Okay. And now we take this integral of total number of particles by I mean, we can still take the integral from 0 to infinity because the zero limit will not contribute to the integral, so it's fine. Okay, so I'm writing the final form. So let's divide both side by volume. So yeah, now it is okay. This is 1 by v z 1 minus z. Okay. And similarly for the PV upon KT, we will have, here also we divide by 1 over v or divide by v, and we get P upon KT equal to minus 2 by upon HQ and the usual terms. And this is for the ground state. We have 1 upon v log of 1 minus g, which we have isolated from the integral. Okay. Now we can see here for ground state, that is E equal to 0, if you put here in this formula of n upon v, let's call this number n0, we get simply z upon 1 minus z. Okay, and if you put equal to 0 in P upon KT formula, what we get is, so this basically this last term minus 1 upon v ln 1 minus g, this can be approximated as, so in place of z, I mean we can find a form of z as a function of n and not, so simply like this we can naught minus n naught z is equal to z, then z is equal to n naught by n naught plus 1. Okay, and we put here in this formula, so 1 minus n naught upon n naught plus 1. and so we get n naught plus 1 minus n naught upon n naught plus 1. And finally we can invert it and write it like this. Okay, and this thing will at most be equal to, so we can approximate n naught plus 1 as n, and this will be order of n inverse log of n. Okay, and for a large n this will be negligible. Okay, so this will be almost 0, so we can neglect this part. Okay, so finally we have for the p upon kt ratio, okay, so yeah, let's write the complete formula. And the integration so we will assume okay, we will assume beta e as x. Okay, so that beta de will be our dx. Okay, yeah, and then we will get x upon x to the power half ln 1 minus 2 e to the power sorry z e to the power minus x dx, and this integration is equal to 1 upon lambda cube g5 by 2 of z. Now this g function is called Bose-Einstein function. Okay, and its expansion is given like this. Okay, and similarly we can integrate the number of particles. So yeah, so we just calculated this last term, okay, which is nothing but n naught yeah, this is just n naught, right? So we will subtract it from the right hand side, from the left hand side, and the remaining integral Again we are taking from 0 to infinity, assuming that the 0 will not contribute to this integral, and this is equal to 1 upon lambda cube g3 by 2 of z. So let's call it equation 1 and equation 2. Okay. Now what other thermodynamic quantities we can calculate? So as usual we can calculate energy density, which is given by the differential of log of this grand potential. Okay. And this is equal to 3 by 2 kT V by h cube g 5 by 2 z. And if you see from equation, and let's call it equation 3, so from 1 and 3 we get a relation between pressure, volume and energy, pressure, volume and internal energy, which is U. This is just 2 by 3 U upon V. Okay. So this is valid for when the temperature of ideal Bose gas drops and the density is very high. Okay. Now let's see what happens to the number of particles when temperature drops to towards 0, like when T tends to 0, what will happen to n number of particles, right? And let's first calculate the number of particles in the excited state. So ignore the ground state. Okay. And that is given by this formula, basically equation 2, right? So Ne is equal to so V will be multiplied on the right hand side, and lambda cube we can write it explicitly. It has temperature dependence and g 3 by 2 z. Okay. So this is from equation 2, and Ne is the number of particles in excited states. Now you can notice here that this fugacity z, which is equal to exponential of mu upon kT, it is a bounded uh, function, right, of temperature. So for from say temperature 0 to infinity, when temperature goes from 0 to infinity, Z varies from 0 to 1, right? And so since this is bonded, so G must also be bonded, right? G is also bonded. And hence uh, and this the maximum value of G is when Z is equal to 1, right? And it increases monotonically from 0 to 1. So at Z is equal to 1, this is given by a Riemann zeta function which is equal to 2.612. So this value is not much important, but just for the sake of completeness. Now what is important here is to see that this excited this number of particles in excited state, it is also bonded, right? So because this is basically equal to 2 pi m kt 3 by 2 upon h cube 3 by 2. This is also bonded. Okay, so n number of number of particles in excited state must be less than or equal to this number. And if the number of particles increases than this number, this quantity, then they will be passed to the ground state, which we have ignored till now. Okay, we have the ground state, but we have not put any particles in ground state till now. Okay, but once the excited states get filled, the particles will automatically go to the ground state. Now what about the number of particles that can be accommodated in ground state? So that will be equal to n minus ne, right? Total number of particles minus number of particles in ground state. And this is unlimited, right? There is no limit here. So this is the number of particles that can be accommodated in ground state, which is more explicitly given by this formula. And so this is the condition of Bose-Einstein condensation, that once you cross this limit of number of particles that can be accommodated in excited states, the particles will move to the ground state. And hence the ground state, hence all the particles will be accommodated in a single ground state, and that we call the Bose-Einstein condensation. So what is the condition for this Bose-Einstein condensation? So condition for the big, so the number of particles should be greater than this quantity, and it has a temperature dependence of 3 by 2. So temperature is T to the power 3 by 2. This is the dependence on temperature. Other things are constant. Okay. So this is the condition if the number of particles in a ideal Bose gas increases from this number, which has a temperature dependence of 3 to the power 2 T to the power 3 by 2, then we get Bose-Einstein condensation. Now if we hold number of particles and volume constant, and vary the temperature, then also we can achieve the Bose-Einstein condensation, right? So there is a critical temperature after which Bose-Einstein condensation can occur for any number of particles and any volume. Okay, and that critical temperature is given by, so we'll just invert this formula in terms of temperature. N upon V 3 by 2 upon 2 by 3. Okay, and this temperature is called critical temperature. So if you take any ideal Bose gas and you cool it down to this critical temperature, you will get the Bose-Einstein condensation. And this depends on if you have more if your density is more, so basically the N by V factor here, if it is more, then you will achieve the critical temperature early on, otherwise you will have to go to very low and low temperature. So we can see that from a simple problem. Okay, so let's do that. Okay, so here is one problem based on this thing. So the question says that Bose-Einstein condensation occurs in liquid helium kept at ambient pressure of 2.17 Kelvin. Ambient pressure and temperature at 2.17 Kelvin. Okay, and the question asks, at which temperature will Bose-Einstein condensation occur in helium 4 in a gaseous state? Okay, so we know that gaseous state will have a very low density compared to liquid helium. Okay, so this temperature would be much lower. The critical temperature will be much lower, and so we have to find what temperature will at which we will achieve this Bose-Einstein condensation in gaseous helium. Okay, and one information is given here is that the density of uh, gaseous helium is 1000 times smaller than that of a liquid helium. Okay, so we can solve it very quickly. We just saw that the critical temperature is proportional to n by v 2 by 3, n by v upon to the power 2 by 3, right? And this n by v is the density. So, and the critical temperature for liquid helium is given here, right? So this is the liquid helium, and we have to find the critical temperature for gaseous helium, and this will be equal to this ratio will be equal to the ratio of density for liquid helium upon gaseous helium. Right? And here it is given that the density of gaseous helium is 1 upon 1000 times the density of liquid helium. So this ratio is basically 1000, right? Or 1000 to the power 2 by 3. Yeah. And so the critical temperature for gaseous helium will be 1000 to the power 2 by 3 times the critical temperature for liquid helium. And this we can calculate very easily. So this is 2.17 Kelvin. And wait. Oh, no. This should be in the denominator. Yeah. Otherwise, this critical temperature will be higher than the liquid helium. 1000 times 2 by 3, 1000 to the power 2 by 3. This will be in some millikelvin, which is much lower than the critical temperature of liquid helium. Okay, so this is one example on how we can uh, solve some problems on Bose-Einstein condensation. So this formula is very important, the critical temperature formula for Bose-Einstein condensation, and most of the problems will be based on this. Okay, so far, do you have any doubt? No one? So I have not prepared much for today. I just wanted to discuss this concept, Bose-Einstein condensation. uh, and I could not find more problems based on this. Uh, but I'll try to find some more problems, and we can discuss next week. Okay, so if you don't have any question, we can close today's session and see you guys next week. So next week we will have this session on Saturday as usual. Okay, so thank you for joining. See you. Bye.